Thank you, and thank you very much for the invitation and for the perfect organization. I really appreciate this conference. I enjoy the talks. Everything is perfect. So I will speak about wave in random media because I've been working on that for quite a long time. And today, of course, in this conference, I will speak about inverse problems in imaging in such situations. So first, before going into the math, I want to motivate a little bit the problem I want to formulate and address. So the problem is imaging, sensor imaging. So you all know you have two steps in any imaging situations. First, the data acquisition. Data acquisition, a source or an array of sources transmits waves through the medium to be probed. And an array of receivers collect the waves that have been transmitted through or reflected by the medium. That gives you your data set. And then comes the data processing step. You take the data set and you process it to get to extract information about the medium. Okay, and as we all know, there are very successful modalities. For instance, ultrasound echography works pretty well. So on the left, you have the data acquisition step with this array of transducers. So transducers can be used as sources and as receivers. So the transducers emit short pulses that propagate through the medium that are reflected by reflectors. And the same array of transducers collect the backscattered waves. So that gives you the data set. And then the processing is very simple to get an image of the reflector. It's very simple because, in fact, it's easy to identify echoes in the recorded signals. And the times of the echoes can be translated into depth because you know the travel times through the medium, because, in fact, you know the background medium. The background medium is very simple. In the human body is essentially water, so you know essentially the background medium. So these kind of techniques work well with very simple processing because the background medium is known. So that's the standard situation. But I would like to consider another type of situation. So typically, again, ultrasound echography, but this time not through the human body, but through concrete. So it's about the same situation. You have an array of transducers. You have the medium to be probed. So the transducers transmit, record the backscattered echoes, and you have to process the data to extract information about the medium. So these are real measurements. So here I can give you the story. In fact, a French company built this thick concrete block. They manufactured holes from the bottom interface. And they did the measurements with ultrasound from the top surface. And they gave the data to a few teams with a question, find the holes. So that was the question. So it seems a simple situation. We all know how ultrasound echography works. But when you look at the data, you realize that the situation is not so simple, because when you look at the data, it looks extremely noisy. You can't see any particular echoes that would come from the holes, the inclusions that have been embedded into this concrete block. So the data looks very noisy. So what is this noise? So you may say, well, that may be measurement noise. Usually, this is what we think about noise. But it's not. And it's very easy to check here that it's not noise, measurement noise, because you can check reciprocity. So reciprocity tells you that the signal recorded by B when A transmits should be equivalent, if it is really a wave, to the opposite. You exchange A and B. And it turns out that you can check that this is the case. Here you have three particular pairs of transducers AB, and you have two traces. The blue one corresponds to A emit, B receives, and the other color corresponds to the opposite case. And you can see that the two traces are equivalent. So this signal is not noise. It's really the impulse response of the medium. So you have information about the medium there. So why is it so noisy? But it's so noisy because, in fact, here the medium is not water. It's not a almost homogeneous or smoothly varying medium. It's concrete, and concrete is made of small grains. And all these grains, in fact, scatter the waves, the ultrasonic waves, so that what you record, in fact, is a multiply scattered wave that corresponds to the propagation of this wave through this highly scattering medium, in such a way that you don't see, in fact, any particular echoes that come from the few holes. So this is a true situation. Now we have the answer. The competition is over. So you can see that, indeed, the situation is simple. You just have 5 holes, and you can't see here 5 echoes that we would see if the medium, the background medium, was homogeneous. So the question is, how do you go from this to that? And that seems a little bit hopeless, but I will show you that, in fact, no, you can indeed process this data in an original way, so that you will go from this set of very, very, very noisy data to an image of the medium. So that's the first application I have in mind. The second one, well, it's not equivalent, but it's in another domain. It's in optics. So this is a standard optical experiment. You want to image an object. So here it's a mask. So typically a double slit. The opticians like double slits. So you do you have here a very simple object, a mask. It is illuminated by, let's say, a laser beam. Let's say a time harmonic plane wave. And you have a camera, a CCD camera. So if the medium were homogeneous, that would be very easy. You would get very simply an image of the mask on the camera. But here you have a strongly scattering medium, really strongly scattering, think at, I don't know, milk, something like that. And as a result, what you record here looks like noise, spatial noise this time. So when you look at the image recorded by the CCD camera, you get something like that, called a speckle pattern. You don't see any particular structure. It's just a bunch, a collection of hot spots and dark spots. And the question again is, if you record this, can you infer the shape of the mask? Can you retrieve the shape of the mask from the speckle pattern that you record here? And it turns out that I will show you that we are not quite there, but almost. We are almost at the position where we can really process this guy to get the object of the mask. So these are the two situations. So compared to the previous talks, you understand that the originality of what I want to do is I consider that the background medium is strongly scattering. So I have to understand how waves propagate through strongly scattering medium. So that's my main contribution. So let's go. I want to understand the forward problem, how waves propagate through random media, randomly scattering media. So I will only consider during the talk, for the analysis, I mean, the scalar wave equation. So you recognize the scalar wave equation with a source term. So let's say for the analysis, I will take a very simple source term, a time harmonic source localized in the plane z equals 0. Think at the ultrasonic experiment, for instance. What is original here is a background medium that is characterized by an index of refraction or a speed of propagation. Usually that guy is considered as either homogeneous, constant, or smoothly varying. It's not what I want to consider. Here I want to consider a spatially heterogeneous medium with small-scale fluctuations that are complicated, that I don't know. I don't know the locations of all the grains of the concrete. So I don't know it. So I will consider that this is a realization of a random process. So something like that. So that's the situation I want to analyze. The medium is a realization of a random process. U, the wave field, is solution of this PD driven by this random process. And I want to understand the structure of the solution of this PD driven by this random process. So I'm not the first one doing that. You have a long history in physics and in mathematics. So in mathematics, in fact, let's say the most successful approach so far has been proposed by George Papanicolaou, even Joe Keller before him, let's say a long time ago. So there is a very nice book giving the state of the art 10 years ago about wave propagation and time reversal in random media. And the key is multiscale analysis. That is to say, you consider the situation you have here. You analyze the situation, and you want to identify the characteristic length scales of the problem. What is the typical wavelength? What is the typical propagation distance? What is the correlation length of the medium? The typical size of the heterogeneities? You collect that. And if in your situation some of these scales are very different, you will use this hypothesis. You will take the ratio of these two scales, go to 0 in an asymptotic analysis. And eventually, you will prove that the solution of this PDE is close to the solution of an effective system that is hopefully simpler than this one. So this effective system may be deterministic. This happens, for instance, in the homogenization regime. You end up with an effective PDE, deterministic PDE, and sometimes it's random. It all depends on the particular regime in which you are. And today, I don't want to consider the homogenization regime because obviously we get random pictures at the end of the day, so it's not governed by a deterministic equation. So I already know I'm not in the homogenization regime, and in fact, the correct regime, which corresponds to the two applications I have described, in particular the second application, is a so-called paraxial regime. So I summarize it in a nutshell like that. So it's a special high-frequency regime. So high-frequency regime because I consider the wavelength is much smaller than the typical propagation distance. So that's high-frequency regime. And additionally, I consider that the correlation length of the medium is somewhere in between. And let's say the radius of the beam or the size of the source or the equivalent is also somewhere in between. So in this particular regime, indeed, I can develop an asymptotic analysis, and I can identify an effective system for the envelope of the wave that is much simpler than the original scalar wave equation driven by a random index of refraction. So first, of course, since the source is time harmonic, the solution itself is time harmonic, so I focus on the spatial envelope. And we can show that this spatial envelope satisfies a Schrödinger type equation driven by a Brownian field. So this is what we call a stochastic partial differential equation. So here there is quite a lot of mathematics to go from the Helmholtz equation, say, to the Ito-Schrödinger equation. So again, it's just a multiscale analysis. You introduce a small dimensionless parameter epsilon that encodes this hypothesis. The wavelength is of order epsilon 4, the correlation length is of order epsilon 2, R0 is of order epsilon 2, and the propagation distance is of order 1. So you plug this and that into the Helmholtz equation, you have epsilon everywhere, and you take epsilon goes to 0. And at the end of the day, you get the Ito-Schrödinger equation. And the Ito-Schrödinger equation is, in fact, much simpler than the original system. Why? Because here I have a Brownian field, and I know Ito's calculus. So I have a huge machinery, a huge toolbox that allows me to compute whatever I want about the solution of this SPD. So it's much simpler to manipulate the solution of this SPD than the solution of the original system. So I assume from now on that I am in the paraxial regime and that the wave propagation, in fact, is governed by this Ito-Schrödinger system. And I will do the calculation, the theoretical calculation with this guy. Yeah. Epsilon here is a small parameter that encodes this. So I say that lambda is of order epsilon 4 compared to L. LC is of order epsilon squared compared to L. R0 is of order epsilon squared compared to L. This is to encode this hypothesis. This is what I have encoded here.
So I want to see the connection between these proof.
This is exactly that. This is to encode that lambda over L is of order epsilon 4, LC over L is of order epsilon 2, R0 over L is of order epsilon 2. And I don't give more details. Look at the papers, but it's a really technical multi-scale stochastic analysis. So now I consider that this is the system that governs the wave propagation. So this is a system. So for instance, the first thing you want to study is the coherent wave or the mean wave, the expectation of the solution. Ito's calculus tells you that the expectation of the solution satisfies the closed equation. This is, in fact, very simple. It's the equation that would be satisfied if there were no randomness, no random fluctuations, and you have an additional homogeneous damping. So that tells you that the mean wave, the coherent wave, is what it should be if there were no fluctuations in the medium, if the medium were homogeneous, times an exponential damping. So that's well known, that the coherent wave is strongly damped in a random medium. And even you can identify here the exponential decay rate. This is what the physicists call the scattering mean free path. So the mean wave decays exponentially as it propagates through the random medium. So that's very important because that tells you that the standard image that we have about noisy data, which is the noisy data is the unperturbed data plus noise, that's wrong. It's not what happens. The real data is 0 plus noise. When you propagate over several scattering mean free paths, the mean wave, the coherent wave is gone. So all methods that tries to exploit the mean wave, the coherent echoes, they are lost. So delay and sum, reverse time migration are not designed to work in randomly scattering media, and they miserably fail as soon as you want to see something, to probe something that is deeper than a few scattering mean free paths. So does it mean that game is over? You cannot do imaging? You cannot see anything beyond a few scattering mean free paths? No. Because what happens is that the wave energy is transferred from the mean wave, the coherent wave, to incoherent zero mean fluctuations. And these incoherent waves contain the information about the medium. So you have to understand how this information is encoded. So the right way is to look at the cross-correlation function of the wave field. So you take the wave field at 2 points, you look at this guy, and in fact, when you do the analysis, you discover that the right way to look at things is to look at the Wigner transform, which is a local Fourier transform of the covariance function. When you look at this guy, again, you use Ito's formula, blah, 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 blah. It's a piece of cake, that's easy. You end up with the fact that the mean Wigner transform satisfies a radiative transport equation. So this is how the information encoded through the covariance function or the mean Wigner transform is transported through the medium. And this information is really transported. It goes much farther than a few scattering mean free paths. It propagates through this equation. So again, this equation were proposed a long time ago by physicists, and you can do the connection between what the physicists do and what you do here using this Ito-Schrödinger equation in Ito's calculus. You can identify what the physicists call the scattering cross-section in the standard radiative transport equation. So that tells you that when you want to do imaging beyond a few scattering mean free paths, what you have to do is not process the data directly, but process the cross-correlation of the data. This is where the information is. And if you observe this, you know the equation satisfied by this guy, so you can retrieve the information. It's a new inverse problem. You have the equation, and you have the data, and you can solve it. So that's the hope, but it doesn't work like that. Why? Because you never measure that. Because of the expectation. You don't measure an expectation. Expectation means an average over all possible realization of the random medium. In practice, you have one realization. So you never measure the mean Wigner transform. What you can measure is the Wigner transform, the same guy without the expectation. That is accessible. You can measure it at the surface, say, you can measure that guy. But unfortunately, that guy is not statistically stable in the sense that the standard deviation is much larger than the mean. So if you measure that and claim that this guy satisfies the transport equation, that's wrong. What you measure does not satisfy at all the transport equation. So the standard deviation is much larger than the mean. So you cannot process directly the Wigner transform that you measure directly from data. And this is very important from the practical point of view. Believe me, when you deal with real data, it's immediate that this guy is completely noisy. So what you have to do is to replace the expectation that you cannot do practically by something. And something means you have to smooth a little bit. You smooth a little bit in R, the midpoint of the covariance function. And you have to smooth a little bit in Xi with, let's say, a Gaussian convolution kernel, but you could take another kernel. So you smooth a little bit the Wigner transform to get the smooth Wigner transform, and you hope that by smoothing, you will get something that is statistically stable. So to check if it is really statistically stable, you will compute the coefficient of variation of the smooth Wigner transform, the ratio of the standard deviation over the mean. And you wonder, when is the coefficient of variation smaller than 1? If it is smaller than 1, that means the standard deviation is smaller than the mean. So a typical value, a typical realization, will be very close to the mean. And then you can use that in the inverse problem given by the system of transport equations. But this is very important. So the question is, by how much do you want to smooth? And you don't want to smooth too much, because if you smooth too much, maybe you will be statistically stable, but you will lose resolution when you solve the inverse problem. So you just want to smooth what is necessary and sufficient. And it turns out that you can compute this guy once you admit that the wave is governed by the Ito-Schrödinger equation, because you can compute all moments, in particular the fourth-order moments of the wave field that are necessary to compute that guy. So I will not show you the expression because it's a little bit complicated, but you can plot it. And in fact, it's complicated, but not so bad. You have a kind of universal picture once you renormalize the two smoothing parameters, the smoothing parameter in position, the smoothing parameters in angle, say, by some number, deterministic number, that depends on everything. And once you do this renormalization, you have this picture that tells you that you should smooth in such a way that you are in this region, that the coefficient of variation is smaller than 1. So you have to smooth a little bit in R, you have to smooth a little bit in Xi, according to this rule, to be in this region to get something statistically stable. And so this rho depends on everything. And in particular, something that is very interesting, it depends on the depth. Very important in practice, we have discovered that you need to smooth the Wigner transform, but depending at which depth you want to image, the smoothing is different. You shouldn't try to find a universal smoothing. Depending on the depth, you have to smooth in a particular way. And since we have the expression of the rho, if you are successful in imaging something at some depth, then you know how you have to smooth at other depths. And this is very useful for our experiment, because in the experiment, we knew one thing. We knew that there were a bottom interface. So first, you image the bottom interface. You find the regularization parameters and everything to image the bottom interface. And then, plop, 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 you know exactly how you have to smooth and how you have to solve the inverse problem everywhere within the concrete block. So this result is in fact very useful. And just to show you, you can indeed now, okay, you have the system of equations satisfied by the Wigner transform. You know exactly how you have to smooth the experimental data to be the data set of the inverse problem corresponding to this forward problem. So now it becomes a standard inverse problem. So you take this data set, you compute the cross correlation, you compute the smoothed Wigner transform with the good smoothing parameters, and at the end of the day, you get an image of the concrete block. So here, we were surprised when so that's the bottom interface. We were a little bit stressed when we sent the result to the company, because we were being told the holes are very simple, and we figured out that there was something strange in the middle of the concrete block, but in fact, there were indeed a complex hole with multiple interfaces that we could detect all of them. So in fact, they were surprised, but we could see everything. So with ultrasound, you can see through 1 meter of concrete, which was not expected, but you can do it. But the data set is the standard one ultrasound echography. The processing is completely different. We don't backpropagate the data directly. We first compute the cross correlation, we compute the Wigner transform, we smooth the Wigner transform in an appropriate way, and we use that in an inverse problem based on a system of transport equation. So it's a completely different inverse problem, and as a result, the resolution properties are not at all the ones you are used to in ultrasound echography, because here the wavelength is, let's say, 3 millimeters at this frequency, 1 point something megahertz. And here you can see you have 60 centimeters. So you can see that this is, okay, let's say what, 2 centimeters. So the resolution is not at all the wavelength or related to the wavelength. It's related to the system of transport equation. So the resolution is not as good, but you see something, while in standard, with the standard algorithms, delay and sum or reverse time migration or this type of things, you don't see absolutely anything beyond, because here the scattering in free path is very short. It's about 5 centimeters. So here you have 20 scattering in free path. So that's why your data were completely noisy. You have only noise in the sense that you don't have any coherent echoes, you don't have any mean wave or coherent wave. Okay, so this is for the first application. Yes, the transport equation. From the Wigner transform, the smooth Wigner transform recorded at the surface. You go back, and indeed, as I said, it was very important for us to know that we had a bottom flat interface. That was the key to calibrate the method. Because we didn't know anything about the concrete. We were given no information about the concrete, the effective speed of propagation, the scattering properties. We knew nothing. So if you know absolutely nothing, you're really lost. But if you have such an information, that's enough to reconstruct everything.
But is concrete, does that satisfy this scaling law?
Not exactly. You are in the high-frequency regime, for sure. Now, the typical scale of the correlation length of the medium is not so far from the wavelength. So you are hardly in the random paraxial wave equation. But again, the analysis is good to understand what happens. Then you design the algorithm, and then you take your data set and you hope for the best. Okay, so everything is based, in fact, it's very important to have first order moments of the solution of the wave equation or the Ito-Schrödinger equation. It's very important to calibrate to get something tractable for correlation-based imaging. As I will show now, it's also important when you go to optics. Why? Because in optics, you don't get time-resolved measurements, you measure intensities. Intensities are more or less the square modulus of the envelope, say. So if you measure the square modulus of wave fields, and if you want to do correlation imaging, all you can do is intensity correlation. So you immediately end up with first order moments. And if you want to characterize the statistical stability of intensity correlation-based imaging, you need 8th order moments. But I will skip that part. Okay, so let's go back to this. That was the second motivation. I have a mask, a time harmonic plane wave, so it's a laser beam, a CCD camera, a strongly scattering medium, and I record a speckle pattern. So it's a zero, detail that, and I want to, from this speckle pattern, image the mask. So in the first modality, I will cheat a little bit. I will assume that I have more data than just that, in the sense that I assume that this guy is moving, and I know the motion. I know exactly the motion of this guy, which means that for each position of the mask, I have a speckle pattern. Then the guy is moving a little bit, and the speckle pattern changes because it does not illuminate the same part as of the scattering medium. So you get different speckle patterns as the mask is moving. And now, from all these speckle patterns, you can retrieve the shape of the mask, if you know exactly the motion of the object. So this is the situation. In fact, for the analysis, it's very simple. Here you have a time harmonic plane wave. So the only difference with respect to the previous analysis is that now you have a parameter R, which is the shift, the central position of the mask. Say. So for each R, you have a particular source term, say, which is the original source term, or the shape of the mask, shifted by R. You can get the intensity of the transmitted wave field for each R. So the intensity is the square modulus of the slowly varying envelope, say. And what I compute, what I extract from all these speckle patterns is the correlation function of these speckle patterns. That is to say, I take one speckle pattern recorded for one position R, another speckle pattern recorded by another position R prime, and I compute the cross correlation between the two images. So that's the correlation degree between the two speckle patterns. Because I observe that when the mask moves just a little bit, the two speckle patterns that I record there are very strongly correlated. It's almost the same. And in fact, in this correlation degree, when you follow this correlation degree, you will extract the information about the shape of the mask. So that's the whole idea, to show that this guy contains the information about the shape of the mask. So you can do the analysis. Okay, so I will show you this formula. That's the first one you get. In the paraxial regime, if you assume that the wave satisfies the Ito-Schrödinger equation, you can compute the expectation of this guy. Because when you take the expectation of this guy, you have force order moments. And we know how to compute force order moments of the wave field. So believe me, you do the calculation, you do your math, and you get this. So in some sense, you are reasonably happy. You are reasonably happy because you can see that indeed F is somewhere, but it seems a little bit tricky to extract the F from that. And on the top of it, I have taken an expectation, which I cannot do. So can you simplify a little bit this? Yes, and that's very surprising. The situation becomes very simple when the medium becomes really strongly scattering. That is to say, the medium is so scattering that the propagation distance is much larger than the scattering mean free path. When you are really strongly scattering and the camera is large enough, in the sense that it records the speckle patterns in which you have many, many, many speckle spots, if these two conditions are fulfilled, first you can show that, let's say, the standard deviation of this guy is much smaller than its mean. So a typical value is equal to the mean. So this is essentially given by this condition, the fact that you have many speckle spots in your image. And this very complicated expression here becomes much simpler. The second term vanishes. You simplify the first term. And up to a multiplicative constant, you can see that the relationship becomes much simpler. It's a kind of square modulus of the Fourier transform of the square modulus of the Fourier transform of F. Suddenly, you get a simple relationship between F and the covariance function. And from that, you can extract the F from the observation of the covariance function. So you can extract. You have a little bit of work to do, because it's an algorithmic part. It's a two-step phase retrieval algorithm. Because from the covariance function that you observe, what can you extract? You see that this guy is in fact the modulus of the Fourier transform of that guy. Okay, so you can interpret that guy as a function that is positive valued or non-negative valued. So you have a non-negative valued function, and you know the modulus of this Fourier transform. So that's a classical phase retrieval problem. If you know a function and the modulus of the phase of a function, and you know the modulus of its Fourier transform, you can implement an algorithm that will recover the function. So you know the modulus of that, of the Fourier transform of that. You know the phase of this function. The phase is 0 because it's a positive valued function. So by a phase retrieval algorithm, you can retrieve that guy. And now, again, if you know that guy, that means that you know the modulus of the Fourier transform of f. You know also the phase of f, because it's a mask function, so it's an indicator function, so it is also non-negative valued. And then you can extract f. So you have a two-step phase retrieval algorithm that tells you that from this observation, you can retrieve the mask function. And very surprisingly, a physicist has tried, it works. But he had to, that was not easy, because these two steps phase retrieval algorithm is really not stable. So they really had to play with numerical buttons, say, to optimize the two steps phase retrieval algorithm to indeed extract the mask indicator function from the covariance of the speckled pattern recorded by the camera. But they did it experimentally, so it works. Very surprisingly, the first time I saw it, I was surprised, but it works. Nevertheless, you can see that it's very complicated. The algorithmic part, when you try to show that the inversion, this is stable, you end up with, no, it's not stable. But it works. I was surprised. So you can help. In fact, you can change a little bit the physics, I mean the experimental configuration to get something a little bit simpler. So in fact, the idea is this one. In the previous implementation, the mask, the illumination was a normally incident plane wave, and the mask was moving. Now let's say that the mask is fixed, but you play with the illumination. You send always a plane wave, but with different incident angles. And you will repeat the whole machinery. That is to say that for each incidence angle, you record a speckled pattern, and again, you cross-correlate, and you see what happens. So again, you compute the cross-correlation between the speckled patterns, say. You compute the expectation of the cross-correlation function. Again, you find a quite complicated expression, a little bit simpler than the previous one already. And eventually, under the same conditions, if the medium is strongly scattering, you discover that this covariance function is related to the mask indicator function, but in a simpler way, in such a way that the processing is much simpler. You look at the cross-correlation, the covariance function, the correlation degree of the speckled patterns. You take a Fourier transform of this guy. So that's stable, and that's easy. That's a direct algorithm. You take a Fourier transform of this guy. That gives you directly the square modulus of the Fourier transform of f squared. And now, okay, the Fourier transform is easy and free from the numerical point of view. From that guy, you can extract f squared by only a one-step phase retrieval algorithm. And this one is much more stable. That's much easier. So you go from a two-step phase retrieval algorithm to a one-step phase retrieval algorithm. Okay, so that's the second one. Now the question is, yeah.
Can you explain a little bit about why the medium suddenly disappear? I mean,
No, it does not disappear. It plays a crucial role. If, sorry?
is to the next order, and you see the medium itself in the correlation?
This is the exact expression that relates the correlation degree of the speckled patterns with the shape of the mask and the medium. The medium is there. So you can see it's encoded there. So here you have the influence of the medium. But the beauty of it is that if the medium is strongly scattering, this guy simplifies, and the medium appears only through a multiplicative factor. No, it's not so hard, because in fact, when the medium becomes strongly scattering, in some sense, that means that this times this concentrates around that guy equal to 0. Because you have a kind of, how can I say? You have a kind of concentration. In fact, the speckled spots become so small that you get a kind of a Dirac contribution in this complicated expression. And then suddenly it's like a Dirac times a multiplicative factor. I will not recover. I just want to identify the spatial support of the mask. I don't want the multiplicative factor. I don't care. And as it becomes essentially concentrated around that guy equal to 0, you get immediately a direct connection between the covariance function and the shape of the mask. And that's really because the medium is strongly scattering. When it's moderately scattering, you are in between the coherent and fully incoherent case, and this complicated expression tells you that, in fact, you don't get exactly this. You have a kind of convolution, additional convolution, that depends explicitly on the statistics of the random medium that is quite messy. And if you don't know the statistics of the medium, in fact, you don't know the convolution kernel, and it's very difficult to get over the shape of the mask. But if you know that the medium is strongly scattering, that helps you. So there are two regimes where you can do simple imaging. It is a homogeneous regime and the strongly scattering regime. And the imaging function is completely different in both cases, but these are the two cases where you can get a simple answer. In between, you don't know exactly where you are. 5 minutes, okay. So here is just a very funny experiment. Because, in fact, you can propose an implementation, a physical implementation, in which what you measure is directly the shape of the mask. So you don't need any phase retrieval algorithm or stuff like that. So it's a little bit tricky. So that's the configuration. So this time, you remember in the previous step, I was playing with illumination, but I was still sending plane waves, time harmonic plane waves with different incidence angle. Now I assume that I send an incoherent illumination, the speckle pattern itself, a very incoherent illumination, that I can measure. So in some sense here I have a beam splitter. So this very incoherent illumination is splitted into two pieces. On this propagation arm, I measure the intensity distribution. And on the other arm, I have the object, and I collect the total transmitted intensity, the spatially integrated intensity. And now I correlate these two guys. So it looks like strange the first time you see the experiment, because you can see I have put my expensive camera in front of nothing. But this is what you have to do to measure, in some sense, the illumination. So now if you do that, so that's the modeling. So you can repeat the whole machinery, scalar wave equation, incoherent illumination with some statistical properties. So to simplify the analysis, you can assume that the sources are delta correlated in space, a very incoherent illumination. You look at the slowly varying envelope. You measure the spatially resolved intensity in the first arm, where there is no object. You measure the spatially integrated intensity in the other arm, and you correlate. So this is your data set. And again, you repeat the whole machinery. You first compute the expectation, you compute the variance, you show that it is statistically stable, and so on. And eventually, yes, you get something in which, at the end of the day, what you measure is almost the shape of the mask function. Almost, because you still have a convolution kernel, but you can specify the width of the convolution kernel. I mean, you can compute it, you can predict it, which means you know with which resolution you can get the shape of the mask. And you can do the calculation in different situations. First, when the medium is homogeneous, you get a convolution kernel whose width is in fact not surprising. It's a standard Rayleigh resolution formula. if you look at what it means, it's essentially L, the propagation distance, divided by the wavelength times the radius of the source. So that's a standard resolution formula. But in an incoherent situation, the illumination is incoherent. If now the medium in the two paths, 1 and 2, is randomly heterogeneous, and I can describe the propagation by the Ito-Schrödinger equation, I end up with a convolution kernel that has a radius. So don't look at the exact expression. Just notice that the radius is larger than in a homogeneous medium, which means you lose resolution. Not so surprising. When the medium is heterogeneous, your image becomes smoother and smoother. You lose resolution. And what is really funny, but for people doing time reversal in random media, that shouldn't be a surprise. If the medium in the two paths is random, but it's the same realization of the random medium, you have something very surprising, that randomness, I mean the scattering, helps you. The radius of the convolution kernel in this situation is smaller than it is in a homogeneous medium. So the illumination becomes more and more incoherent in some sense, and that helps you. And you can get an enhanced resolution in this situation. So that's very funny to get this situation, because we had found such a result a long time ago, more than 10 years ago, about time reversal. But this is the first time we get such a result in an imaging situation, which is very different from a physical time reversal. And yes, that's a funny idea. So in fact, I'm not developing that. The Institut Langevin in Paris is developing that. Is the following idea. Remember here, we were thinking, okay, we use an incoherent illumination, so in some sense, we have to measure it. Okay. But now assume that indeed you use an incoherent illumination, but you control it. So how do you control it? You use this device. You use a spatial light modulator, but instead of sending a very nice slide, you send a speckled pattern. But you know it. You know what you emit. In such a case, you can compute the intensity distribution that should arrive there, because there is no object. So since you can compute it, you don't need this path. You control the illumination. You use a numerical wave solver. It's just a Schrödinger equation. So with one Fourier transform and one inverse Fourier transform, you compute the field. So you know how to compute the intensity distribution that should be there. And then you just need to correlate this numerical intensity distribution with what you record there. And that means that by controlling the illumination, you have an imaging setup in which here you have only a 1 pixel camera. You use a 1 pixel camera and you get a very nice image of the mask. And it has been done, so not by me, so I will not show you the result. I will let Matthias Fink show you the result. But this is very surprising, but it works beautifully because, in fact, he told me that it's very easy to implement this because these spatial light modulators are well known and controlled. The numerical wave solver is very simple. A bucket detector is nothing. So it's very easy to do this and to check that indeed a 1 pixel camera can give a high resolution of a mask. And I like this situation, that will be my final slide, because I told you at the very beginning, I work on wave propagation in random media. That's my main field of interest. And often we are being asked, so in fact, does random scattering helps you or not in communication or in imaging? And the answer is not always simple. And in this experiment, you have all possible answers at the same time. That is to say, if you put a randomly scattering medium here, that means that it is common to the two paths, then this guy is good for you. The more scattering the medium is here, the better it is for the quality of the image. If you put random medium there, then it's bad for you. The more scattering the medium is there, the worse is the image. And if you put random medium there, it doesn't play any role, because all you collect is a spatially integrated transmitted intensity. And as long as you are not in the localization regime where the wave is backscattered, if the wave is fully transmitted, even in a current way, it doesn't change anything. So this random medium plays no role. So here you have a strange situation. In a single experiment, random medium may play very different roles depending on where it is. So that's very funny. This is a very nice experiment to play with, because there are so many degrees of freedom that you can come to different conclusions depending on the particular setup you are considering. And I'm just on time. I thank you very much for your attention.
Thank you for this presentation. Are there some questions? Okay, one.
Yeah.
Still trying to understand about the medium disappear there. So if the medium is invariant in the X plane.
It's a three-dimensional medium. Huh?
I'm sorry?
It's a three-dimensional, means...
Yes, because I mean, I assume you mostly care about the, I mean, if this is the Z direction.
Yes.
If my medium is constant, I mean, just say...
It's not a randomly layered medium. It's really a three-dimensional.
Yes.
Because you can see it when I was saying, trying to explain from here. Here you see more or less this gamma is a transverse covariance function of the medium. And when I say you have to show that the transverse covariance function is maximum at 0 and decays very fast, that means that you have strong transverse fluctuations. Right. This is what I want to say. Huh? When I say this concentrates as this quantity equal to 0, that means that gamma, which is a covariance function, is maximum at x equals 0 and decays very fast.
Right. Yes, so my question is that if it's independent in this direction, go away directly from the formulation. You know, if gamma is independent of the...
Is constant if you have a randomly layered medium in some sense?
Only in this direction.
Yes.
Then
it disappears. That's bad. You will not see any image of the mask.
Okay.
No, you need a three-dimensional random medium. That's very important.
I suggest that maybe you can continue the discussion. Maybe we have the space for one or two short questions.
Can you go to the last?
The last slide, this one?
So you have medium 1 and medium 2.
Yeah.
Do I understand correctly that they must be identical? They can be random, but they must be the same.
No, if they are not the same, then you will lose resolution according to that.
So
if they are the same, you gain resolution. If they are independent, you lose more and more resolution as the medium becomes more and more random.
I'm just trying to understand. If you have one signal traveling through 1
Yeah.
and another through 2,
Yeah.
and you correlate then the transmitted signals,
Yeah.
is that identical to having the same signal after time inversion traveling back to the single?
No, because anyway, here you only record intensities, so I can't really time reversal works when you have time resolved measurements and you can really send back the fuel wave. Here I only measure intensities. This way, something. So I can't really do that. In fact, the idea is that, of course, something I have not said, I should have said, the distance from the beam splitter to the mask is exactly the distance from the beam splitter to this camera. So in some sense, you would like to measure exactly the illumination that arrives just before the mask. That's the idea. So when the two media becomes independent, what you measure here is correlated but not fully equal to the illumination that arrives there. But if they are equal and strongly scattering, that means you have a strongly scattering illumination just there, and that's very good for you. And you know it. If you measure it and the two media are equal, you measure exactly the incoherent illumination that arrives at the mask.
Okay. Thank you. We will stop here the questions. Thank you again.